kicking things and running into things, and I spilled coffee on myself in the car.
It's really the beginning of the day.
Okay. Today's the 7th. It's March 7th. That feels like it should add up to something. I don't know what. 3/7/17. Anyway, energy is the ability to do work. Ability which you may or may not have on a given basis. So if we have that bowling ball that's rolling that has some amount of kinetic energy, can it exert a force on another object moving that object? Yes. When it exerts a force on another object moving another object, what has just happened? It has done work on that other object. Duh. Who here has gone bowling? I just found out we have a bowling team. I think that's awesome. We should go bowling. Let's just cut this and go bowling. That bowling ball, when it strikes the pins, it exerts a force on them, it moves them, it does work on them. It has kinetic energy, and it uses that kinetic energy to do work on another object. Kinetic energy is the ability of a moving object to move something else and do work on it. Okay, Katie, what were you saying?
Mass velocity.
1/2 mass times velocity squared. Okay, which piece is more important in terms of the kinetic energy of an object? Velocity, by far. So, and there we have 1/2 k equals 1/2 mv squared. So the velocity of an object is much more critical. A ping pong ball moving at high velocity can have the same amount of kinetic energy as a bowling ball moving at a lower velocity. Velocity is really critical to this. The faster something is moving, the more energy it has. Okay, so F equals ma, W equals F delta x, W equals ma delta x, and we have this old kinematics equation. We can solve it for a delta x, and we have Vf squared minus Vi squared divided by 2. So far, so good? You probably have to write this down in order to get it. You can't do algebraic derivations by following along. I promise you this. So, if we plug this in for the a delta x, we get W equals m times the quantity Vf squared minus Vi squared divided by 2. Okay, well that doesn't seem so ugly. We can distribute the m. We can take that divided by 2 and distribute a 1/2. We get work equals 1/2 mvf squared minus 1/2 mvi squared. Are you starting to see anything that looks familiar from what we just talked about with kinetic energy? mv squared, 1/2 mv squared, 1/2 mv squared. Oh. Uh-huh. Guess what work's equal to? Something's final kinetic energy minus its initial kinetic energy. When your bowling ball is rolling down the lane with some amount of velocity and it hits the pins, does its velocity change? Yeah, it does. We can measure the work that's done on the pins by the ball in terms of the change in the ball's velocity. Whoa. That's cool. What you're going to find is that in this chapter you get offered some shortcuts to information from chapter 3. Big, long, hairy, crazy, ugly trajectory problems that you did the hard way, we suddenly have an easy way to solve. Oh, but you had to know forces stuff first. Okay, we're going to quickly walk through this derivation by hand. You got these two, and you're good with it. So I'm going to orange highlight, whoops, and plug in. We now have so far so good. Okay. Now we have Vf squared equals Vi squared plus 2a delta x. Yes. If we want to solve for a delta x, we can do Vf squared minus Vi squared divided by 2 equals a delta x. I'm going to shrink all of this a little bit. And remembering the exact path of the derivation here is it's definitely not as important. I know for me, my brain works better that if I can see the derivation, I get it better, which is why I force you to do derivations, because I suspect that's true for a lot of you. Okay, I'm just going to finish this because we're this far. So now we have W equals mass acceleration, mass times Vf squared minus Vi squared over 2. We're going to distribute that across. W equals mVf squared minus mVi squared, all divided by 2, which means, of course, that we are multiplying them each by 1/2. 1/2 mVf squared minus 1/2 mVi squared. So the work is equal to its final kinetic energy minus its initial kinetic energy. Huh? Okay, so what this means is that work is equal to the change in kinetic energy. Because this, and somehow the subscript got lost, is Ke final, and this is Ke initial. So the net work is equal to the change in kinetic energy. This is called the work kinetic energy theorem, and it says that when an object does work on another object, the work that's done by that object is equal to the change in its kinetic energy. Its mass stays constant, we hope. If its mass is changing, then you have to employ some calculus tricks, and we're doing algebra-based physics here, so we're not doing that. Be thankful. What this allows us to do is solve problems using the change in kinetic energy. So we're going to do 5b. Not exactly. Okay, so for plain old kinetic energy, we're going to look at sample problem 5b together. And this is a 7-kilogram bowling ball moving at 3 meters per second. We want to know what its Ke is, and then to think about that comparison between a ping pong ball and a bowling ball, how fast must a 2.45 gram table tennis ball move in order to have the same kinetic energy as the bowling ball? Is this speed reasonable? So we have this here equation for Ke, 1/2 mv squared, 7-kilogram bowling ball. It's pretty easy to figure out the Ke of the BB, and it is a 7-kilogram bowling ball.
I was just going to say, can we put a B subscript on there?
Okay, we've got it all set up. Oh, and this is, of course, squared. So 7 times 9 times 0.5. The kinetic energy of the bowling ball is 31.5 what? Joules. We want the kinetic energy of the ping pong ball to be the same as the kinetic energy of the bowling ball. And what we want to know is what speed does the ping pong ball have to achieve to accomplish this? So we're going to solve for velocity. So Ke pp, for which we have a value, equals 1/2 mv squared. So we have 2 times kinetic energy of the ping pong ball divided by mass is equal to the velocity that's required. I skipped a bunch of algebra steps, but I think 4-part algebra, you guys can all follow that. So we plug it in. Okay, so we've got 2 times 31.5 joules divided by 0.00245 kilograms, because of course that was 2.45 grams. So 31.5 times 2 divided by that. Yes?
It's just what that says. Above the box on the left, the square root on the left. What is that, K-E?
K-E-P-P. There. So we get the square root of 25,714.28, blah, blah, blah. We get a velocity of 160.356 meters per second. The second question they ask, is that a reasonable speed for a ping pong ball? Heck no. Remember that, like highway speed is about 30 meters a second? So we're talking here about, 4 times 60 miles per hour to put it in terms that Americans can understand? Yeah, this is the speed of an airplane, basically. You're not going to accelerate a ping pong ball to 160 meters per second. I see that one island has decided that this is like a flag thrown down, challenge accepted. Okay, knock yourselves out. I didn't tell you to do it. Wear eye protection for the love of Pete. Okay. I'm going to let you guys do, so 5B are just kinetic energy problems. You're going to like them. They're super stinking easy. They're all assigned. So 5B, page 174, all. And that's where we will stop for the day.